Well, thank you. We are staying online with our next presentation, and we have this time two presenters. We are now focusing on the techno-economic analysis and life cycle assessment of the C123 process. And we have Jordy Motte and Mohamed Mahmoud already connected. Hello.
Can you hear us? Hello?
Yes, hello.
Yeah.
Hello, good afternoon and welcome. A few words about you two before you present us the result of your research. So Mr. Jordy Motte, he studied bioscience engineering at the Gent University and is currently a PhD candidate at Gent University, Belgium, completing his research next month. And he's mainly investigating the sustainability of alternative production pathways for C3 chemicals. He also performs life cycle assessment and exergy analysis for the C123 project. And Dr. Mohamed Mahmoud, who earned his engineering doctorate in process design from the Eindhoven University of Technology, and now a process design and development consultant at the Process Design Center. He leads projects on biochemicals, energy efficiency, biofuels, hydrogen, waste treatment, and recycling. He is currently involved in multiple collaborative research and development projects, including C123, where he is responsible conceptual design and techno-economic analysis of modular scale processes. I will pass the voice to you to present the conceptual process design, techno-economic and environmental assessment of the C123 modular processes. Thank you.
Thank you, Veronica, for the introduction. I will get right to it. In this presentation, I would like to share with you the conceptual process design, techno-economic evaluation, and environmental assessment of the C123 scenarios for the modular processes. So what's the story with the modular processes? There is a lot of underutilized methane-rich feedstocks around the globe. And these feedstocks typically are smaller feedstocks, so they're not actually large scale. And this makes it very challenging for the state-of-art technologies that currently are available for the methane valorization to be feasible, to be utilized in these feedstocks. And these feedstocks can be in various forms. It could be in a biogas, which is typically smaller scale production facility, and or can be flared in various locations as associated gas. So there's a lot of associated gas flaring around the globe, and also marginal field gas. So there is a lot of marginal field gas that available that they're not close to industrial facilities and they're far away from locations, so they're not being utilized. So the idea of the C123 project is to design technologies that can actually valorize these smaller feedstocks. And these technologies in a model scale, so a production capacity of 10 to 30 kiloton of the product. So the idea is to capture these methane resources and convert them through OCOM, oxidative coupling of methane, in a combination with the hydroformylation into a chemical that can be transported and further converted into another product. So this is the story of the modular processes in the C123 project. To give you a closer look in the process concept, so typically for this is the first scenario, which is scenario A, which is conversion of biogas as a feedstock. The biogas typically contains a lot of carbon dioxide, so that's why the first step in the process is to remove the carbon dioxide through amine wash, which is a state-of-art technology available in a large scale. And then, yeah, as I mentioned before, the core of the technology are the OCOM reactor and the hydroformylation. And these are operating in various pressures. So that's why we have a compression unit in the middle. And typically, the hydroformylation operates at equimolar ratios between the ethylene, carbon monoxide, and hydrogen. Ideally, the OCOM should produce these ratios, but since, yeah, there's nothing ideal. So from that perspective, what we try to do with the catalyst is to push the catalyst to produce ethylene and carbon monoxide in one-to-one, and we let the hydrogen to be a kind of degree of freedom to see if we can produce that. So in the OCOM as well, we produce ethane, and that's why it's going to be cracked using the post-bed cracking to produce more ethylene and hydrogen. And as we produce more hydrogen as well, there's excess from the outcome with respect to carbon monoxide. So we use the water gas shift reactor as a balance for that. So what we do, we try to produce more hydrogen and balance the ratio between the carbon monoxide and the ethylene. So this is basically the upstream section, if I can call it like that. The hydroformylation is very sensitive to oxygen, the catalyst. So that's why we have a small molecular sieve bed to absorb the oxygen. And then everything goes to the hydroformylation. It's then being converted to the aldehyde, the propanol. And the second step is that we absorb or we extract the propanol or separate it using extractive distillation and send it to the hydrogenation reactor to produce propanol. Part of the propanol used as a solvent for the extraction technology, and the light gases is further then recycled back to the process. So this is just an overview of the process. Two important consumables for this process concept is the oxygen, which is actually supplied using partial PSA unit, which is pressure swing adsorption. And then the hydrogen needed for the hydrogenation and for adjusting the hydrogen ratio for the hydroformylation is we use electrolysis for that. So this is a quick overview of scenario A. The process is not very different when it comes to the marginal feed gas. The idea is that for the marginal feed gas, which is usually located in a very remote area, and for this case, we assumed, Russia as an option. There's a couple of marginal feed gas available there. The most interesting thing about the marginal feed gas that there is ethane present in the feed. And the idea that if ethane is present in the feed, it's not actually a good idea to put all this large amount of ethane in the Occam reactor. So the first thing we do here, we crack first the ethane in the post-bed cracking, and then we recycle the light gases, and the Occam has higher concentration of methane in the feed than the fresh gas composition. But the rest of the concept is relatively the same. The third scenario, which is the associated gas, is the most challenging scenario, in my opinion, and that's due to the large amount of ethane present in the field. And this is actually data from existing associated gas field in North Dakota in the United States. And in this case, the concept changes a bit because in this case, it's kind of like two plants at the same time as like oxidation plant and at the same time ethane cracking plant. So we put everything in the ethane. Put all the feed in the post-bed cracking, where we crack the ethane to ethylene and hydrogen. And we use the POX partial oxidation reactor in this case for production of carbon monoxide and hydrogen as well. But in this case, since we have a lot of ethane, we crack the ethane and the methane as well. We have extra hydrogen, and that's why we thought, you know what, let's not use cryogenic units because it's not really favorable at this small scale, all model units. And it's better to just oxidize the hydrogen to water, which we're gonna knock out anyways in the compression and the drying stage. And this is the third concept. When it comes to the modular scale plant itself, so it's basically a smaller standardized prefabricated models. And you can think about them as exactly as these Legos to the side. Basically what you do, you break down the plant into smaller units that can be easily prefabricated and ready. And you just go on site, you put them there and connect them together. So I like this picture because it literally makes the visualization very clear. From a perspective of the advantages of these model plants, that it allows us to utilize a smaller scale because the economy of scale is very challenging at smaller scale. But with this unit, you can actually use a number up approach to offset this effect. And another option, another advantage of these model scale units, that since they are built offsite, it allows us to build them, to just connect them. It makes it easy to construct the plant, especially when you're at a very remote location, such as in the marginal field gas or the associated field gas, when it's very difficult to construct an entire plant and erect the whole columns. So that's the concept. Another value could be is that the flexibility of the technology is very flexible with respect that we can easily modify it. You can take the whole plant, you build it, and if the feedstock is gone, you can disassemble the plant and you can actually put it somewhere else. So it's very flexible and it's easier from construction point of view with respect to time and cost and safety as well, since you don't have a lot of workers working on site to build this long, big construction for the plant. So it's easier. So there's no injuries and easier to transport and ship around. The main design consideration. So when it comes to design consideration, we're targeting 10 to 30 kiloton per year. And the size or the dimensions of these models should not exceed a shipping container. So each unit or each model should not be, you cannot have like 20 meter length column. Its maximum is 12 meter and with a certain weight. And as you can see, these dimensions of a container. But then it's very important in this project, especially when it comes to the model or processes, that we need to maximize the selectivity and the conversion, because this is help us minimizing the intermediate separation steps. And of course, means if you have less separations, automatically the process become more cost effective and more efficient. This is how you can combat the economy scale of issue. And as well, it allows us to make it more portable, because then you can actually just ship them and move them around, and they're easier to be integrated. So all these options are considered, and these factors are aspects being considered in the design of the model scale plant. I want to walk you quickly in the techno-economic assessment. These actually are preliminary techno-economic data because currently the final model that we have, or the final concept that you've just seen, is currently being modeled. So just give you an idea of where we were, and hopefully when we get the public report, you can see where we are right now. So this is the approach. So we start with the mass energy balance and the simulations. We use Aspen modeling for that. From the mass and energy balance, we can size the equipment and the units, and we calculate as well the capex. And for the manufacturing expenses, we use the labor cost and the raw materials, and everything is converged in the end into a product cost of propanol. This is just a screenshot of the capital cost. At that stage, we didn't distinguish between B1 and B2 from feedstock perspective, so we just call them scenario B. And as you can see here, the cost of the per model cost is not the whole capex, actually. There's a lot of other costs, and this is the purpose of this slide, just to show you that, okay, the capex include contingency fees, land costs, site development, auxiliary buildings, and a lot of other things. And these factors actually is rule of thumbs that we use and common practice in the industry. This is a breakdown of utilities and raw materials of the scenario. And what you can see here, that the majority of the utilities for this scenario is basically electricity, cooling water, natural gas. And here, when it comes to the raw materials, the majority of the cost is biogas in this case, and some oxygen. It's a bit different in scenario B because especially in scenario B2, where you have associated gas, the majority of the raw materials is oxygen supply with the PSA, because we assume it's kind of outside the battery limit. So it's just there is an existing unit that can produce or generate oxygen on site, and the natural gas is free. So this is an advantage for this scenario. On the other hand, yeah, it's very similar with respect to electricity and cooling, and natural gas is not in the picture here because you have a relatively very small amount of money for that, or you can even get it for free. When it comes to the manufacturing expenses, here a screenshot of the whole manufacturing expenses for the two plant. And as well, the manufacturing expenses are made from or constructed of direct costs and indirect costs and general expenses. And all these costs are included in the final calculation of manufacturing expenses, even the depreciation of the equipment. And you can see here the final manufacturing product costs for these two cases. This is the summary of the techno-economic assessment for the preliminary data that we had previously. And what you see here, we have scenario A and scenario B. And what we want to show you that the production capacity is the effect of economy of scale. And you can see here the production capacity increased from 13 to 30. And this is directly affect the product cost. So at higher production capacity, you have smaller product cost. And at the same case here. And the idea is that here in these results, what you see is quite optimistic, because that we were really at early stage at that time. And yeah, this could go way higher. This may be what we're going to see after we cost the final product. Thank you so much. With this, I conclude my slides, and I will give the floor to Jordy.
Thank you, Mohamed. So in the second part of this presentation, I will present the some preliminary results of the life cycle assessment for the C123 project. So I will focus on two different methodologies in the presentation, the environmental performance assessment and the resource efficiency analysis. Next slide, please. So first I will explain the methodology of the environmental performance assessment more in depth. So the goal of this assessment was to compare the different C123 scenarios. So the scope was from cradle to gate. That means that the use and disposal of the final product is not included in the analysis. For the functional unit, we have chosen 1 kilogram of propanol, and we also assumed that this propanol has a high purity of 99.5%. We have selected different key performance indicators for the comparison, such as global warming burden, the energy input, water consumption, and human health damage. Then finally, for the data collection, we have done some simulations in Aspen to derive mass and energy balances for the C123 production steps. And then for the supporting processes, data was collected via the literature and the EcoInvent database. The next slide, please. Then the second methodology was the resource efficiency analysis. This analysis can be conducted at two different levels, so at the life cycle level and at the process and plant level. At the process level, we have performed exergy analysis. So exergy means the useful part of the energy. For all inputs and outputs of a production step, we could calculate the exergy value. And this, based on this information, we can calculate then the exergetic efficiency of each production step. At the life cycle level, we have used the SEEN method that is developed by Professor De Wolf. So SEEN stands for the cumulative exergy extraction of natural environment. So basically, this means the amount of resources that is extracted from nature, such as fossil fuels, water, nuclear energy, and so on. So based on the SEEN value, we can calculate then the exergetic efficiency at the life cycle level. Next slide, please. So here on this slide, you can see the preliminary results for the environmental performance assessment. So I've selected the result for global warming burden. So what you can see on the figure is that the third scenario, where we start from associated gas, has the lowest impact on climate change. So this can be explained by the fact that we avoid flaring in this case, because flaring generates a lot of greenhouse gas emissions. This is the only scenario that also has a lower impact than the conventional one, propanol production. However, at this stage of the project, we still have to be careful with this comparison, as the C123 scenarios and the conventional production has a different technology readiness level. So the main contributors to the impact is the biogas production and upgrading in scenario A. So this can be explained by the high amount of biogas that is needed to obtain 1 kilogram of propanol, and also the substantial amount of energy that is needed. In all scenarios, we saw that the oxygen production has a high share for the impact on climate change. So also the electricity production, the direct CO2 emission in the CO2 reduction stage, and finally also the heat production for preheating. Next slide, please. Here on this slide, you can see the results for energy use on the left axis and the percentage of energy that comes from fossil resources on the right axis. So this percentage is indicated with the red dot on the figure. So here you can see that the production of 1 propanol from biogas has the highest energy need. But on the other hand, this scenario has also consumes less or fewer fossil resources than in the other scenarios. The next slide, please. Okay, so now we can also have a look at the results of the resource efficiency analysis. First, I show you the results for scenario A, where we use biogas. So the color codes on this figure have a different meaning. The red blocks correspond to the C123 production steps, and the green blocks correspond to the supporting processes. The flows represent the exergy content of each flow. So the wider the flow, the higher the exergy content. So in the red blocks, we can see that the exergetic efficiency of the C123 production steps is quite high. So it's between 90 and 100%. However, the exergetic efficiency of the biogas production is much lower. That amounts to 13%. And then finally, if we look at the exergetic efficiency on the life cycle level, so for the whole life cycle, then we see that it amounts to 6%. A final conclusion from this figure is that the exergy content of the recycling stream is quite big. So this recycling stream contains methane. That means that we have to try to increase the conversion of methane into 1-propanol so that we do not use exergy due to recycling. Okay, next slide, please. And then here on this slide, you can also see the result for the last scenario where we use associated gas to obtain 1-propanol. So this scenario has a higher life cycle exergetic efficiency. So here it amounts to 28%. So that's higher than in scenario A. However, an important side note is that we make use of renewable resources in scenario A, and this can also be part of a circular economy because we make use of waste fractions of the agriculture sector. So that's important to take into account. Next slide, please. Okay, so then we can have a look at the conclusions of this presentation. So we showed you a process concept that can utilize widely available and wasted methane sources via modular units. So these modular units are easier to design and build. This can lead to some cost reductions, and it's also easier to modify and transport. The main challenge that Mohamed is still facing is the economy of scale. So this could be solved by the number up approach. From the environmental assessment, we can conclude that scenario B2, where we start from associated gas, is the most promising. Because this scenario has the lowest impact on climate change, and it has also the highest exergetic efficiency on the life cycle level. However, we still make use of a fossil resource, of course. Okay, next slide, please. That was it from our side. So thank you for your attention. And if you have some questions, please ask.
Thank you both. Yes, let's start first with our room questions in our room. We have one question for both.
Thank you both for your very interesting presentation. I have a question for each one regarding the techno-economical analysis. You showed a very complicated flow diagram of the whole process. Have you identified which is the most the most resources demanding step apart from the catalyst? Is there any other, like let's say the separation of oxygen? I don't know.
Yeah. Thank you so much for the question. If I understood correctly, you're asking about what is the most expensive or most demanding unit of operation or step.
Yes. Yes.
Yeah. The thing is, from a process point of view, the most challenging, actually, and the most demanding is the carbon capture unit. Amine units are standard technologies that are available, but at this scale, especially in smaller scale, are really expensive. So we were investigating alternative options such as membranes and processes actually to think about, okay, if we can use it, because what's interesting about this technology or this process, that we don't need to remove all the carbon dioxide. The idea is we can allow some carbon dioxide in the streams moving around. So yeah, it's still under investigation, but the problem is we have to deal with that. Another issue is the catalyst itself. One of the catalysts is, especially for the higher formulation, is quite expensive. So these are the two, let's say, bottleneck in addition to the electrolysis unit. From energy perspective, because we could actually go for steam methane reforming, as an option for hydrogen production, but the idea is to look into technologies that need to be developed or new technologies that renewable sources. And that's why we thought about, okay, let's use electrolysis, and especially now the cost of the renewable energy is going down. So this makes the electrolysis in the future, when this technology reaches commercial stage, it would be interesting from that perspective.
Okay, thank you.
Thank you.
And, as you mentioned about the carbon dioxide, I saw from the life cycle analysis that the environmental impact in some cases is not positive. But what about the CO2 emissions? Is it the same, follows the same trend, or in some cases you can have smaller CO2 emissions and higher overall environmental impact?
So the question is on the CO2 emissions in general.
The carbon dioxide emissions, just this, not the whole environmental assessment.
I know. So we also looked at other indicators such as human health damage, for example. So there we doing a good job actually, because we avoid the emission of particulate matter or carbon monoxide, which is occurring in the flaring processes. Yeah, and of course, in this moment, the global warming burden of the C123 process is still higher than a conventional production, but we can improve some things in the process. For example, heat integration is not included yet. So we have to use external heat. If we could, for example, make use of the heat from exothermic reactions in the process and produce some steam out of it, then we can reduce the CO2 emissions. Okay. So it's still preliminary results at this moment.
Okay, thank you very much.
Thank you both. Yes, there is one last question online. Before I will present this to you, is there anyone else in the room who has any questions for our presenters? Then I'll move on. Instead of electrolysis, wouldn't it be more advantageous to use well-established commercial technologies such as steam methane reforming, SMR, for hydrogen production?
Yeah, as I mentioned before, I think what's interesting about this technology, or the purpose of the C123 project, is to look into non-conventional technologies in general. And the steam methane reforming has already been developed, it's already been there for a long time. So we looked into the option of using electrolysis as an option for production of hydrogen. And of course, it's more expensive technology. Even the cost of hydrogen production through electrolysis is more expensive. But what we know about SMR is very efficient on a large scale. But since we're talking about model units, electrolysis by itself is inherently modular, which is actually fits quite well the technology itself from the C123 technology. So yeah, the cost is going to go down in the future with respect the renewable cost energy. So considering the time frame and time to market perspective of this technology and commercialization path, we opted for electrolysis instead of other technologies. Thank you so much.
Thank you for covering our questions and your presentation today, presenting the result of your research. I think that these are all the questions we have for you, and thank you again.
Thank you so much.